I'm going to look at the change in my y values. So change in my y values is going to be f of x plus h minus f of x. And that's the change in my y values over the change in my x values, which is x plus h minus x. But when we want to do differentiation, we want to make h as small as possible because we want to know the gradient at that very point almost. So what we're saying is, let's make h approach really, make it really small and approach 0. And so when we simplify the denominator, we get x plus h minus x is going to be h, and we take limits of that as h tends to 0. So a quick little recap. If we think about so I might have done that by mistake. If we think about f of x as being x squared, if I wanted to differentiate this from first principles, dy by dx equals limits as h tends to 0 of f of x plus h minus f of x over h. Now, how's this going to work? So, limits of as h tends to 0, x plus h, f of x plus h is going to be x plus h squared, because if my input is x and I square it, if my input is x plus h, I'm going to have to square that. Minus f of x is x squared all over h. And so if I sort this out, I get x squared plus 2xh plus h squared minus x squared all over h. And so limits here as h tends to 0. If I simplify this, this and this cross out. I've got 2xh over h plus h squared over h. This crosses out with this. This crosses out with this. And so I'm taking a limit of as h tends to 0 of 2x plus h. At this stage, all we're doing is replacing h with 0. H is so small that is insignificant. So this then becomes 2x. And that is why if y equals x squared, dy by dx equals 2x. This is actually the process of differentiation from first principles. What we have learned to multiply the power down and take one away from the power is a shortcut to doing it from first principles. Does that make sense? Right, okay, so now what we are going to move on to next is trig differentiation. So before we can go on to trig differentiation, just want to recap a couple of things. We were looking at radians. In radians, right at the end, one of the things that we covered was small angle approximations. And you might remember that I asked you to put in input different values of x which were close to 0 in radian mode. And I said sine theta is approximately equal to theta. And cos theta was approximately equal to 1 minus theta squared over 2. So these were the small angle approximations, and you have to know this in order to do trig differentiation from first principles. So So with that in mind, I want you to maybe have a go at differentiating f of x equals sine x. And of course, theta has to be in radians here, or x has to be in radians. You can only do the same big letters here. Trig differentiation only in radians. Okay, does not work in degrees. Okay, so here I want you to try and do this from first principles. My starting point is to say f dash of x equals the limits of as h tends to 0 of f of x plus h minus f of x all over h. So then I'm going to say limits of as h tends to 0 of sine x plus h, because if f of x is sine x, then x plus h, my input now is x plus h, so this is going to change to sine x plus h, minus sine x all over h. So this is your starting point. Right, what I want you to tell me now is what shall I do next? What shall I do next here? Yeah, very good. Not sub into 0. I'm going to sub in 0 into h at the very last step. I have got an expansion of sine a plus b essentially here. Okay, so now what I can do is say limits of as h tends to 0 of my a is x and my b is h, so I get sine x cos h minus, sorry, not minus, plus cos x sine h. And that's the expansion of this sine x plus h. I've still got minus sine x all over h. Does that make sense? Is everyone happy with that? Now, what can I do at this stage now? What do I do at this stage? This is where I need to start using my small angle approximations. So I know sine h should be h, and cos h should be 1 minus h squared over 2. So we're going to say because h is small, it's approaching 0, I can say sine x is sine x, I can't change that. Cos h is going to become 1 minus h squared over 2 plus cos x times my sine h is going to become simply h, right? And you might be wondering where I'm getting these from. That's what I wrote in this. So if I replace theta with h, sine h is going to become h, cos h is going to become 1 minus h squared over 2. So I get up to here. Now what? So at this stage here, I still need to have minus sine x, and it's all over h. And I need to expand, simplify. Limits of as h tends to 0. I expand that in, I get sine x minus h squared over 2 sine x plus h cos x minus sine x all over h. Okay, so all I've done is expanded the brackets for sine. Now, at that stage, we can cancel this out with this. And so now we are left with limits, no, I'll put a divide there. Limits of as h tends to 0, I've got minus h squared over 2 sine x over h plus h cos x over h. Okay, so is everyone happy with that? Now, when I do h squared over 2 divided by h, I'm going to cross out one of these h's with the h squared. And for the second term, this h is going to cancel out with this h. So then I get limits of as h tends to 0, minus h over 2 sine x plus cos x. So I need to take the limit of this squiggly bracket here as h approaches 0. And as h becomes 0, 0 times by this thing is going to disappear. So as this term disappears, this term is not dependent on h. The only thing I'm left with is cos x. And that's my answer. So that then tells me that if y equals sine x, dy by dx equals cos x. And that is what we have found out by doing this process. This is like a 4-mark question, to be fair. So, you know, it's 4% of a paper. Why were only the h terms turned into small angle? Very good question. The reason only h terms were turned into small angle because we're saying as h approaches 0. That's how you work out gradients. Yeah, and that's the only reason h terms were approaching. We did small angle approximations for that. Okay, any other questions? Right, okay. So now that you've seen a process, I want you to differentiate f of x equals cos x from first principles. Just do it in red. I want you to differentiate this from first principles and let me know what answer you get as soon as you're done. I'm going to give you about 5 minutes to do that in, please. So, looking at this, oops. F dash of x is going to equal limits of as h tends to 0, cos of x plus h minus cos x all over h. So what's the first thing I'm going to do here? I'm going to do the expansion of cos x plus h. So limits as h tends to 0, cos x cos h minus sine x sine h minus cos x all over h. Now, what's the next thing that we are going to do? H is a small angle. So I can do small angle approximations of this term and this term. And we know what the small angle approximations are. So I want you to go ahead and do the rest of it yourself. Let me know what answer you get as soon as you're done, or if you get stuck along the way, please, very important that you communicate with me. Right, okay. If you do have anything, well, let me know. So now we can use these results, very important to be able to use these results, unless it says from first principles, we can go ahead and say, well, if y equals sine x, we can quote the result that dy by dx equals cos x, and if y equals cos x, dy over dx equals minus sine x. Okay, so these are results that you can quote. You don't need to prove them every time now. Each of these here is made up of more than one function. Now, that is known as a composite function. So, for example, you might have had f of x equals sine x, and g of x equals 3x. And actually, sine 3x is the same as saying fg of x. Fg of x is sine 3x. We'll come back to composite functions when we actually go back over functions properly. But composite function basically means one function inside another function. And the key to differentiating composite functions, just a second. The key to differentiating composite functions is something known as the chain rule. Okay, so chain rule is used to differentiate composite functions. Now, how does the chain rule work? I'm going to show you, first of all, the proper way it works, and then I'm going to show you the shortcut on how it works, so that you've got both methods there to exploit as and when you feel right. Now, let's look at y equals sine 3x, for example. That's what we started off with. This is causing a problem because I've got a 3x here instead of a normal x. We know how to differentiate sine x, that wouldn't be a problem. But this is a 3x. So what we're going to do on the side here is say, let u equal to 3x. And so y then becomes sine u. Would you agree with that? Any questions there? Yeah, so if I let u equal 3x, I'm going to replace 3x with u. Now, the chain rule simply is that dy by dx, you can get to dy by dx, for example, by doing dy over du times by du over dx. This is one form of the chain rule. All the chain rule is saying is you can make dy by dx by multiplying or dividing different versions of dy by du and du by dx in any way you see fit. So let's see how this is going to work out. If I write du by dx, what is du by dx? Please tell me in the chat. What is du by dx? So u is 3x, and du by dx is going to be equal to 3. That's good. I've got dy by du. If y equals sine u, what is dy by du? I know when I differentiate sine x, I get cos x. If I differentiate sine u, I'm going to get cos u. Is everyone happy with that? Okay. Okay, perfect. So if I've lost you at any place, stop me and let me know so that I can go through any bits that you're finding, because obviously first time you do something is tricky. Yeah. So now I've got dy by du, I've got du by dx. Now I can use the chain rule. So here is my chain rule. My chain rule is to say dy by dx equals dy over du was cos u, and du over dx was 3. So I get 3 cos u, which is then going to become 3 cos 3x. And that's my answer. And that's my chain rule done. So what we have realized is that if y equals sine 3x, and dy over dx equals 3 cos 3x. That's very good. So if we have composite functions, what we're doing is we're sort of splitting each bit up, differentiating each bit and multiplying them together at the end. Right, okay. So now you are going to have a go at, maybe I'll give you some time to copy that down and make sense of that. And after you've done that, have a go at y equals cos 3x plus 4. And let me know what you get once you're done, please. So I've got this funny bracket here. So my first substitution is going to be let y equal 3x plus, not y, u, because I've already got y in there. So u equal 3x plus 4. And so du by dx is going to equal 3. And now, if I think about my y is going to become cos u. So dy by du is going to be minus sine u. And the product, not the product, the chain rule is simply that dy by dx is dy by du times by du by dx. Because what's really happening is that this du is going to cancel out. And that's why we're only going to be left with dy by dx. But we can exploit that relationship now. Dy by du was minus sine u. Du by dx was 3. So we get minus 3 sine u, which is going to become minus 3 sine u was what we originally started off with, 3x plus 4. So this u is 3x plus 4. Are you happy with that? Does that make sense? If you have made any mistakes, where the mistakes are happening. What is our transform? What's our u going to become? Our u is going to become let u equal to this complicated thing inside the brackets. So essentially, we're always trying to get to a simple bracket. so that we can differentiate sine u. So u equals x squared plus 3x. So y then becomes sine u. And we know how to differentiate that. And that simply is dy over du equals cos u. That's what we understood from our first proof of sine x. If I differentiate u, I get du by dx equals 2x plus 3. And now all you need to do is multiply the two together. So dy by dx equals dy by du times by du by dx. And so dy by du was cos u. Du by dx was 2x plus 3. I'm not going to put this in brackets like that. I'm going to say cos u times by 2x plus 3. And so I'm going to move that to the front. 2x plus 3 cos u. And we know what u is. It's x squared plus 3x. And so this is what we get. Now, can you check that against what you have and identify where, if you have made a mistake, where the mistake happened? And tell me in the chat as well. The answer for this would have been 2x cos x squared plus 3x plus 3 cos x squared plus 3x. Okay, so that is equivalently correct. That's not wrong. Okay, that I've just got it in a simpler format here. Now, what is wrong? So here I'm going to write the wrong answer. If you wrote 2x plus 3 cos x squared plus 3x, that would be wrong because we need to multiply all of this by cos of x squared plus 3x. We need the brackets, and that's why this is wrong. Okay. Right, okay, so now you're all sort of recognizing where your mistakes are happening. Now, what have you spotted when you differentiate? So what we've realized here is that if y equals sine of x squared plus 3x, we get dy by dx equals 2x plus 3 cos x squared plus 3x. Okay, so now that's what we've realized here. Yeah, very good. So what we have realized in each case, if you look back at your notes, you're going to realize a pattern. And hopefully you're going to get to the pattern before me. So if y equals sine of f of x, can you summarize for me what is, you can do it in one step. You don't need to do that whole long drawn out process. You can do this in one step. What should I write down for dy by dx? What's the general formula? What we see here is that when I differentiate x squared plus 3x, I get 2x plus 3. So if I differentiate f of x, I'm going to get f dash of x multiplied by sine. The differential of sine is cos. We get times by cos. But this bracket stays the same. So we get f of x. And that is the general formula for differentiating sine f of x. So looking at this, here's my f of x inside the brackets. If I differentiate that, I get 11 minus 2x. And I differentiate sine, I get cos, and this bracket stays the same. And there is my answer. It's as simple as that. So if you get really complicated functions, maybe I might use the chain rule from first, sort of doing all the steps. But otherwise, if it's something like this, you know what to do. Now, the only thing I would say is remember to put this in brackets. If you don't put this in brackets, you've done it wrong, because it's not only minus 2x that's being multiplied by cos of some function. That is the key bit, brackets around f dash of x. Right, okay. Now if we think about on the right hand side, the differential of this, very similar. I might do it in 2 steps just so that you can see it very easily. When I differentiate f of x, I get f dash of x. When I differentiate cos, I'm going to multiply it by minus sine. The bracket of sine or cos does not change, so I'm going to have f of x. And if I simplify that, I get minus f dash of x sine of f of x. And there is the general formula for differentiating cos of some function. We said that if you've got a constant at the front, when you differentiate it, you just multiply it right at the end. So what I'm going to do, I'm going to have dy by dx. This 4 is a constant, it's multiplied by the whole thing. So I'm going to leave the 4 there, and I'm going to differentiate cos 7x cubed minus x squared. Now that is minus, and then f dash of x is 21x squared minus 2x. And then I've got differential of cos is sine, and then I've got 7x cubed minus x squared. And so when I multiply 4 in there, I can leave it as minus 4 times by 21x squared minus 2x sine of 7x cubed minus x squared. Or equivalently, you could have multiplied the minus 4 in there and said something like minus 84x squared plus 8x sine 7x cubed minus x squared. Okay, does this make sense? You're right, let's have a look. So when you differentiate cos, don't forget, when you differentiate y equals cos x, dy by dx was equal to minus sine x. And that's where the minuses come from here. Okay, so that sorts that problem out.